All right, ladies and gentlemen, so this lesson is on related rates. And if you study anything in college where calculus is required, this type of reasoning is probably why it's required for this particular major. So we're looking at how two quantities are changing together. I use this type of reasoning a lot in economics. You use it a lot in most types of engineering. It's super, super useful in a bunch of different fields. So take a second, pause here, and read the question if you haven't already. So what we're imagining, right, is somebody's pulling this ladder out from under you. So the end of the ladder is moving away, and of course, if the ladder is staying the same length, it has to slide down the wall. Here's an animation that would connect this, right? So we see two quantities are changing. We have the distance the bottom of the ladder is from the wall, and the height of the top of the ladder. And they seem to be related, right? As one increases, the other decreases. So these problems can have a lot going on. I have this mnemonic device to help you remember sort of the steps and help you organize yourselves for these. The way you recognize one of these problems is that it asks how one quantity is changing and tells you about another. So how fast are we falling? So how fast is the height of the ladder changing? At the instant the ladder is 7 feet from that house. So that's how we know it's a related rate problem. So you'll learn to recognize these pretty quick. So the way you're going to tackle these is by making notes about what you're given, what you're going to find, and then writing an equation to relate the two. So I want to start with my picture, and if you don't have a picture, you should draw it, probably. I'm going to call this bottom quantity x, right? So x is going to be the distance to the bottom of the ladder is from the wall. I don't know what it is, but I do know I am given dx dt, so the change in that distance with respect to time is 2 feet per second. So that's in the text and in the diagram here. My unknown is going to depend on the question. So the question is, how fast am I falling? Well, if that's called r, and I want to know how fast the rate of change of r, that's going to be dr dt. And I want to make a note of when I'm interested in. So when x is 7, right? So that's part of the question as well. And then my equation, this is often the hardest part because you have to come up with it on your own. So notice I have a right triangle here. So I'm going to say my equation is x squared plus r squared equal to 25, right? Because it's Pythagorean theorem. So anytime you have a right triangle, that's a fair bet. And we'll look at some other examples with some different equations related to this problem here in a second. Now solve. Here's where your implicit differentiation work comes in handy. So the way we think of these problems is every variable is changing as time changes. So that's why I wrote dx dt, right, and dr dt here. They're both functions of time. So that means when I solve, I'm going to use chain rule. So let me show you what that looks like. So there's a reason we're doing this right after implicit differentiation because it looks really similar. So every variable that I have is a function of t. So that means the derivative of x squared is 2x times dx dt. R squared is 2r times dr dt. And the derivative of 25 is 0. So now I have an equation that relates the rate that the ladder slides down the wall and the rate that it slides away from the wall, right? And I know some information about my equation already. So my next step is to plug some of this stuff in. So I know that x is 7 and dx dt is 2. So it'll be like 2 times 7 times 2. And I've plugged in my x and my dx dt plus 2r dr dt equals 0. This all ends up being 28. And then what I get, right, is an equation that relates dr dt and r. Now, unfortunately, right, it seems like I'm stuck, right, because I have two variables, and only one equation. But remember, dr dt is what I'm trying to find. R, I need it, and I can figure it out. So remember, I have this equation, and this is where we're going to look real smart. And I know that x equals 7. So I can be like 7 squared plus r squared equals 25 squared.
And that's going to spit out my r. And I'm going to do that work. You can do that work on your own. For sure, I'm just using Pythagorean theorem and solving for a variable. That gives me r equals 24. And then I can plug that back in. So I get 48 dr dt equals negative 28. And then I divide both sides by 48. And I apologize for not giving you enough room here, but I get negative 0.583. And we're talking about feet per second. Right, so now I've solved for this rate that the ladder is sliding down the wall. And it makes sense that my answer is negative, right? Because my ladder, remember, was sliding down the building. So the key step here, and what really makes this hard, right, is sometimes you have to go back and solve for another quantity you need. And you're doing real math right now, so you're going to have to be like a little bit creative in that you have to come up with the equation on your own and figure out how to get the quantities you need on your own. We're going to set up just a couple more examples so you can see how these problems change depending on how we change what you're asking. So here we have the same problem. We have a right triangle, and we have x and r, and we want to know when the ladder is 4 feet high, how fast is the angle the ladder makes with the ground changing. So I'm going to call that angle theta, which is a little circle with a line through it, because that's just what we use to represent angles. So my given, again, is that dr dt is 2 feet per second. My unknown is, well, how fast is the angle changing? Well, that's going to be d theta dt when r equals 4. And then my equation, well, my equation needs to relate theta, r, and x, right? So here I need to use a trig function because I have an angle and two sides of a right triangle. So I'm going to be like tangent, and tangent is opposite over adjacent. That's why I picked it. So here's where these trig functions come back. It'll be like tangent of theta equals r over x. And now we're going to solve, and this derivative is harder, right? So the derivative of tangent is secant squared of theta d theta dt, and that's our unknown that we're trying to find. And then on the right, I have a quotient. So I'm going to do quotient rule. So x is the bottom times the derivative of the top is dr dt. And then minus the opposite, which is r dx dt, over the bottom, which is, x squared, right? So notice I don't have to necessarily manipulate this, but I can start to plug things in. And again, I'd have to go back and figure out what x equals, and I'll leave that to you. And then we'll take a look at one more example, and we're just going to set it up again. So what is the rate of change of the area when the top of the ladder is 2 feet high? And this is kind of a weird problem. We wouldn't want to know this in real life, but I just want you to see what it would look like. So we're given, again, we still have that same dr dt is 2 feet per second. Our unknown, well, that is, we want the rate of change of the area, dA dt, at the top of the ladder is 2 feet high. So that's r equals 2. Our equation, well, we need to relate the area to the sides of the triangle. So our equation is area is 1/2 base height. And in this context, that is area equals 1/2. We call them r and x, right? And then we need to solve. And this time we have a product, right? So we're going to be like, okay, the derivative of area is dA dt equals 1/2. I'm going to just factor that out. I'm going to be like r times dx dt plus x times dr dt. And then I could make my substitutions and solve, and then I have to go back and solve for quantities I need. So that's the move here. So set them up. using formulas you already know, and then start to work it using your implicit differentiation skills.